Hi, my name is Nitay. I work at Facebook. I'm working on the graph processing team, which is part of the larger sort of data infrastructure organization. So before I begin, how many of you have heard of Giraph, of Apache Giraph? Oh, nice. Okay, so that's about half of you. And how many of you have actually used it, like have run a job, have processed graphs? Like 3 of you. All right, hopefully we'll change that. So my talk today is going to be focusing on how we scaled it, how we got it to the point that it is today. And you'll see that we've made some tremendous improvements and gotten it to very large scale. So first I'll give a bit of background so that everybody can be on the same level and everybody will be able to raise their hands. Then I'll dive into all the scaling work that we did. Then follow up with some results and show some benchmarks and things like that. And finally, some Q&A. So first, some background. So what exactly is Giraph? So Giraph is an Apache open source project that's based on a paper by Google called Pragle. So as many of you probably know, Hadoop is based on GFS and MapReduce, and HBase is based on Bigtable. Similarly, Giraph is based on Pragle. One of the things I want to point out right away that's very important is that, so Facebook is one of the sort of, at least currently, one of the larger committers to this project, but we don't actually maintain any internal fork. We don't have our internal code base. We don't have anything like that. We're working completely off the Apache code. We work with Jira. We work with all of the great tools. That's what we use. So everything that we use, you guys can use. We work off the trunk. So Giraph supports Hadoop, Hive, HBase, Cumulo, and we're constantly sort of adding a lot of other things. Right now we're working on Tinkerpops and a few other things. And specifically for Hadoop, we actually support a wide variety of Hadoop, all the way from like 0.20 without security to Cloudera's Hadoop to Yarn to a bunch of things. Basically, we're trying to be as agnostic as we can about Hadoop. So Giraph specifically is built on a BSP model, and BSP stands for bulk sync parallel, which is this parallel programming paradigm that essentially takes a large computation that you have, splits it up into epochs, and each epoch, the work is divided amongst all the workers. Each one does their sort of sub-computation. They send messages to each other, but, and this is a very, very crucial point, the messages don't actually get delivered until the end of the epoch, and they'll be available for those nodes during the next epoch. We specifically call epochs super steps. You may think of it like an iteration in the graph. And because of this sort of nature, when you send the messages and the ordering and all that doesn't really matter anymore. It sort of removes all the constraints of total ordering and partial ordering and all these sort of concurrency issues that you'd normally have. Giraph has a bunch of tools and things that you may be familiar from Hadoop, like combiners. We have aggregators that let you compute things globally on the whole graph, so you're able to basically infer something from the graph as a whole. You can mutate any part of the graph during the computation. You can add edges, remove edges, add nodes, completely wipe away and like put in a new graph. You can do pretty much anything you want. And all we actually impose on the user is basically specifying to us, what does your graph look like? So you tell us, what do you want to store? What's the ID of a node? How do you define a node? How do you find it? What value is stored at each node? What value is stored at each edge? And what are the messages that are sent between them? And all those are types that are completely generic. They're Java parameters that you pass in. And the only thing that we enforce is that they have to implement Hadoop writable. And that's so that we can serialize them and move them amongst. But other than that, it's completely up to you what you want to do. So very importantly also, what is Giraph not? The first one, this is one that we get confused about all the time on the list, is it's not a graph database. It's not Neo4j, and it should not be compared with that because it's trying to approach a completely different problem, which is very large-scale processing, batch processing, not this sort of live interactive querying sort of stuff. It's also not a completely asynchronous generic MPI system. So because we know that you're working with a graph, and because we know that graphs are sparse, and we know that most of the time you only really want to send messages to your local neighbors, that allows us to do all the various cool things that we do, and allows us to give the user a much simpler API to work with. But it also means it's not just some arbitrary MPI system. And finally, most importantly, it's not a slow tool. This maybe was true maybe a year or two ago, but as you'll see from this talk, it's no longer the case. So one question we get all the time, especially in Facebook, being humongous Hive users, is why not just use Hive? And Basically, the reason is that in Hive, everything breaks down to a map-reduce job. And as we all know from map-reduce, map tasks read from disk, do some key value transformations, write it back to disk, do some shuffling, sorting, then you have reduce tasks, and that writes it out. That in and of itself wouldn't really be that bad. The problem is if you're going to do some graph algorithm, every single step in your graph algorithm is going to become an iteration, and each iteration is going to become its own map-reduce job. So if you have some graph computation that needs to do 1,000 steps, well, guess what? Each of those is its own map-reduce job. So you now have at least 2,000 or so disk seeks and reads and writes and whatnot. So Giraph breaks down into a few components. Each Giraph job has a master. It's very important to understand that when you launch a Giraph job, these components spin up. And when you take it down, that's it, Giraph is gone. We don't maintain our own server or anything like that. We run on top of Hadoop. We launch as a map-reduce job, so to speak. But really all we do is just take the map portion, do our work, and that's it. There's no reducer. There's nothing else. Like we basically use Hadoop for resource management, for launching jobs. And once we're across that point, which is the very beginning, we'll say, OK, Hadoop, thank you very much. We're going to do all our stuff now. So the master synchronizes the super steps. It's basically the one in charge of making sure of enforcing that BSP model. It's the one that tells that makes sure all the workers are doing their computation and sort of blocks at that barrier so that everybody has finished their computation at the same time. It also, between super steps, is the one that's responsible for assigning the partitions between the workers. So we talked about mutability briefly. If you change the graph in some drastic ways and all of a sudden one worker is really unloaded, he can move around the partitions so that you rebalance the load. The workers are the guys doing the actual computation. So each worker is going to be assigned some set of vertices from the graph. As you see here from this picture, there's sort of 4 regions, 4 partitions. In this picture, they're sort of clustered together, but they don't particularly need to be. The simplest partitioning we have is just hash-based partitioning, in which case it would be just scattered throughout. And each worker handles also the input and output, reading various splits, and then eventually writing them out back to wherever your output is. Each Giraph job also has a Zookeeper that we use, and this is to help coordinate everything and maintain sort of a base level global application state that keeps things running smoothly. When you launch the job, you can tell us that you have a Zookeeper cluster already, and we'll use that. But if you don't, it's fine, and we'll spin up our own Zookeeper. So basically, we'll grab a couple of the map tasks, and they'll just run Zookeeper. So the data flow of a Giraph job. When the job spins up, and this should look very similar to map-reduce type of things because we tried to make it very intuitive for users coming from Hadoop. The master takes the input format, splits all the input coming into a whole bunch of splits, assigns them to the workers. The workers each in turn go and read those splits, and they're also assigned which vertices, which partitions they own. So as they read the split, they read, let's say, a vertex at a time. They know, hey, this vertex is mine. I'm going to put it in my sort of data store. Or actually, this vertex belongs to this other guy. I'm going to send it over to him. So they exchange vertices amongst themselves until everybody's done and everybody has the vertices that they're owning, that they're in charge of. Next comes the main phase of the job. And at this point, in this compute and iteration point, there is no more disk I/O. That's it. We've loaded the graph. Everything from here on out is in memory, it's network, and that's it. The partitions of the vertices are, as we said, are owned by workers. Each one does their computation over that, and then they send stats back to the master so that it sort of knows what's going on. Again, does the rebalancing that we said, and can proceed as it needs. One thing to note is there's no sort of correlation necessarily between splits and the partitions. You can have 5 partitions, but 5 million splits. They're unrelated concepts. Finally, when the computation is finished, each worker is in charge of writing its partitions back out to the disk, and then there's an output committer similar to Hadoop. We actually use sort of the same naming format, but instead of like a key value input format, you'll have a vertex input format. Instead of like a key value output format, you'll have a vertex output format. So instead of knowing how to write a key and a value, this user-specified class knows how to write a vertex. So another sort of representation to give you the state diagram sort of things. This is the same as the data flow slide. You see here you have input, you have the super steps looping, and then the 2 things that can possibly halt the computation is either the master says, OK, I'm done, and basically it just halts the entire computation for everybody, or each vertex, when it's done with its sort of local computation, can say, OK, I vote to halt. And when all the vertices have voted to halt, then the computation also comes to an end. And we'll see some examples of how that works. So each vertex has its sort of life cycle, where everybody starts out active. When they vote to halt, they become inactive, which means that the next time around, if they're inactive and they have not received any messages from anybody else, they basically won't be computed over. But if you're inactive and somebody sent you a message, then it's your job to sort of wake up and compute over that and see if there's some new piece of information. So let's see how this plays out. So we have a very simple example, which is I have this basic graph of 3 nodes, and I want to compute what's the maximum value in this graph. And I basically want every node by the end of the computation to have this maximum value. So in the first super step, basically the logic at a single node is I'm going to send my value to all my neighbors. And then when I receive messages, if the messages are received, or if any of them are bigger than my value, I'm going to store that value, and then I'm going to pass it on. Otherwise, I'm just going to go to sleep. I'm going to vote to halt, essentially assume that I have the largest value. So we see after the first computation, after the first super step, that the top node goes to sleep. It basically says, all right, I have the biggest value because all it gets is the 2. The middle node is a value 1. It gets the 5. And it says, oh, wait, the 5 is bigger. All right, I need to store that. The bottom node gets the 1. And it sees that that's smaller than the 2, so it actually goes to sleep. And here's where the interesting part happens. Now there's another, the blue lines are the barriers. Now the 5 gets sent down to the 2 node. It wakes up again and says, hey, wait a minute, here's a larger value. Stores that. And then finally, all of them have halted, and at this point, the computation stops. So this is the actual code to run this. This is not some made-up thing. This is in the Giraph code base. You can go, you can look. This is it. This is all you have to write. And actually, this example is not so contrived, because you can use this code, this exact code, to compute what's called connected components on graphs. And connected components basically tells you if you have a big graph and it's actually made up of subgraphs, you can essentially label them basically by the largest vertex in that one, and this can be used to basically find communities. Another popular algorithm that people always talk about is PageRank. So this is popularized by Google. Basically, it's to find the importance of web pages in a graph or some documents with link types of things. And the idea is that each vertex sends to its neighbors an equal fraction of its PageRank. It's assumed that every link is sort of the same weight. So you can arbitrarily go to any link. Then you compute your new PageRank according to this formula that PageRank has. We can, in the interest of time, I'm going to sort of read through this, but if you're interested about it, I can talk about it in more detail. And one of the interesting things that we looked at for this particular one is, all right, well, in the existing systems, how would I implement this if I didn't have Giraph? So one of the popular ones that everybody knows about is Mahout. And we looked at Mahout, and this is the code to implement PageRank. It's great, it works, it does a decent job, but it's not the most user intuitive. It also has various other issues with performance. This is the Giraph code, and this is it. And if you look at the formula and you look at the code, you can pretty easily map this to that, right? You can actually see the formulas right there. You can see everything before that is sort of summing up all the messages, and you can see everything after that is sending it out. And that's it. So let's talk about how we got to scale, how we grew Giraph. So one of the sort of first things we ran across is as Giraph jobs get bigger and bigger, naturally they run with more and more workers. Naturally, one of those workers is bound to crash. So Giraph has a system called checkpointing, where essentially you can decide every few super steps to actually write out the state. And the state is saved. In case a worker fails, then it can restore from that state and continue on. So that if there's sort of a trade-off between how often do you write, because obviously this adds some hit to the runtime, but you can sort of see how often your machines die and choose the best number for you. Similarly, the master can crash. And for this, we use Zookeeper. So Zookeeper has a great recipe called a queue, and essentially the way it works is when we spin up, a whole bunch of nodes say, when we actually initialize the job, a whole bunch of nodes come up and say, hey, I want to be the master, I can be the master. And one of them wins, one of them becomes the master. And if that master during the computation dies, then the next one in the queue kicks in and it takes over. And actually all the state that the master actually needs to know is fairly small, so we actually keep it in Zookeeper itself. And what this means is the master is completely stateless, essentially. And if it dies and the other one picks up, it can just read that state back from Zookeeper, get everything it needs to know, and compute onwards. Keep going. Sorry, so to be more specific about this, so the slide where we talked about the three components, the master, worker, and Zookeeper. Zookeeper itself is a quorum that's fault tolerant. And so putting all three of these together, we now have a system that has no single points of failure. If any of these components fail, the job still continues, the job goes on. So another thing that we ran into very quickly is that most graph algorithms, even though we allow the user to do whatever they want, and you can put entire maps and collections and huge things inside your vertex values and edge values, most algorithms are actually fairly primitive in terms of the data types that you need. Most of them have, if you're doing like shortest path, you have doubles on the nodes, you have simple integers doubles on the edges, simple integers on the nodes themselves. Similarly for like network flow, if you're just counting some degrees, you might not even need anything on the edges at all. So a lot of graph algorithms use very simple types, integers, longs, doubles. And when you're growing and you have each worker, processing on the order of a billion or so vertices and edges, this becomes a huge hit because collections of primitive types basically have a lot of overhead to them. You have to box and unbox every single time. They're no longer just an int. It actually becomes an object. That object has like a Java's internal monitor, has basically all these other things that you don't really need or want. And the solution here was to use a library called Fastutil. We stuck this in. It's basically a collection of a whole bunch of primitive collections that don't adhere at all to the Java API, because to adhere to the Java API, you have to use generics. You have to return capital long, capital double. But because they don't, they are super efficient. They use primitive types. They use like the actual bytes everywhere. And this saved us a huge, huge load. Still, even with this, we still had a problem of many, many objects. So one specific example we can look at, I came up with this for this talk, is let's say we had a problem if we want to find out during this Berlin Buzzwords conference who's sleeping during these talks. So what I mean by that is let's assume that each user has some labels of basically some potential label of what he thought of a given talk. So it was amazing, it was boring, it was enticing, it was confusing, I slept through it, whatever it is. And you label each user, the ones that you know about. So I may know that the ones in the front most likely thought it was okay, but the ones in the back, they may be sleeping. And I built some graph where basically the connections between the graphs are, let's say, maybe they're friends, or maybe somebody's sitting next to each other. Basically things that I may think those things may influence somebody. So it's not clear to me what the people in the middle, how they think about the talk. And I run this algorithm called label propagation, which basically takes these initial labels of people that I know, sort of how they behave, propagate it through, and then you see sort of at what probability that the unknown nodes did have each label. You basically end up with this probability distribution. So when you do this, and this graph is very small, but what we wanted to do is get these types of algorithms to a very, very large scale. We're talking 1 billion nodes, 200 billion edges, serious numbers. So this particular algorithm with this data, to take this example, we have 1 billion vertices, 200 billion edges. Let's say we're splitting it out over 200 workers. So that means there's 1 billion edges per worker. And each edge, as we can see here, is a double. So that's one object per edge. That's one primitive or whatever it is. So that means per node, with the initial sort of data structures we were using, just a basic old list of edges, that's around, that should be 1 billion objects. Similarly, we have sort of a similar formula for the vertices. So we had a map that contained the vertex data. So we have about 5 million vertices per worker, 10 objects in the vertex value. The reason I say 10 is because, as I was saying, when you get the final result, you get sort of a distribution. So we see like node 5 is going to have some percentage likelihood of thinking that it's amazing because it was connected to node 1. It's going to have some probability of thinking it was boring because of node 4. And we decided that we want to keep, say, the top 5 of those. So each of those labels is one object, and the probability is another one, so 10 objects. That's just throwing out numbers. So then the thing that sort of gets heavy is the messages themselves, because in the message, you have to also send out that distribution to the guy that's ahead of you. So that also is going to be 10 objects per each edge. And on average, you're going to basically send one message per every single edge. This is one interesting point about this type of algorithm, label propagation, versus like the connected components I talked about, is this algorithm on every single superstep everybody always sends a message. Whereas with connected components, the vertices go to sleep, and that means that as the algorithm proceeds, it necessarily does less and less work. That's not true with this. In this type of algorithm, the iteration time stays roughly the same each time. So we have this formula here at the bottom that basically tells us that this total thing uses about on the order of 10 billion objects, which for a single node for Java is huge. At this point, Java GC just starts going crazy. And we have this node that tells us sort of roughly how much the objects are used given a certain data set. So the solution here that we came up with was basically to throw everything out the door and just go back to basics and replace everything with a byte array. Store all the vertices, store all the messages, store all the edges in just one ginormous byte array. And on top of this, we put an iterable interface with this thing that we call a representative object. So that basically, as you're reading it in, the orange sort of pentagon that you see is this representative object. So that would be a vertex or an edge or a message. As you're reading it in, you would write, the user sort of behind the scenes is writing to that vertex, and then we write it to the byte array. Then you write to the next one and rewrite it to the byte array. Similarly, for the interface, when the user is computing over messages, we give them an iterable of messages. That's the interface that Giraph has. And that iterable of messages behind the scenes actually only has a single message. That single message, when you call next, reads in the next data from the byte array, and now you have that data. What this means is if you were to say in your computation, store each one in a list, at the end of the day, you'd have 1 billion or 10,000 or whatever messages that are all the same reference. So the user sort of has to know this, and then if they really want to store every single message, they're going to have to make a copy. Most of the algorithms that we've seen, you only really need to touch a message once, because most likely you're aggregating some data. At the end of the day, what this meant is that we could take everything down, and all the memory that got used on the system sort of came down to this big O of capital V, which is the total number of vertices, which is enormously small compared to, because basically the thing that we found was most of Giraph algorithms are limited by the number of edges, because on average, the number of edges is, say, on the order of 100 times bigger than the number of vertices. So once we got sort of the big capital E out of this equation, it was a serious performance gain. So as beautiful as all of this is, and it really is very cool, everything that it did, it also had an additional savings of not only did it reduce the number of objects, but it also reduced the actual memory, which wasn't even necessarily like originally the intention, but it did that as well, because again, it got rid of those like monitors and all those things that objects have. It just kept just the raw data that we want in the vertex. So this sort of created a new problem for us, which is that we used to work with these lists of vertices and maps of edges, and the type that the user wanted was the type that we already had in memory. Now suddenly everything's in byte array, and we have to serialize and deserialize constantly. So that suddenly becomes an issue of like, well, how do we do that fast? So we started looking at all these things with the interface that we provide to the user is this data input, data output, which is what comes with Writable, with Hadoop Writable. So we looked at various serialization schemes, Cairo, Thrift, etc. And the thing that we came up with is this thing called unsafe. If you guys have not heard of unsafe, it's a sort of hidden piece of the Java API. And when I Googled it, this is what I found out about it. It's dangerous, it has no formal API, it's volatile, it's bound to break, it's non-portable, it's only in the Sun Oracle JVM. And it's so extreme to this point that it's even hard to like actually get at it. And this is the code that you have to write. When you Google unsafe, everybody has this code. You basically have to use this reflection magic to actually pull out where is that freaking object. So all that said, this thing is awesome. This is as fast as it gets. I mean, if you dive down deep into like Cairo and into these serialization libraries, and you find the really, really good ones, you'll see that somewhere they have this code. Like grep, I'm telling you, go to GitHub and grep for the unsafe, and you'll see which serialization libraries are good. And the reason for this is because basically this is as native as it gets. Essentially what it's doing under the hood, you can think of it, the way I like to think of it, is essentially like a C pointer cast. You have a byte array, it says, okay, it's actually a long pointer, I'm going to dereference that, and get it out. I have a friend of mine on the team who's sort of like a JVM expert, and he tells me that these days, the JVM is so good at doing unsafe that it actually becomes basically a no-op. For those of you that are curious, unsafe also comes with a lot of other things. For example, you can allocate memory that's off the heap, not off the heap, sorry, off the JVM, off the garbage collector. And this is how things like direct byte buffers, they actually use unsafe under the hood to allocate the memory. You can also do really crazy stuff, like you can actually inherit from a final class. So you can make your class inherit from like a string, let's say. That one I really don't recommend. So another one that we ran into, I mentioned this idea of aggregations. Aggregations let you compute things on the whole graph. So originally aggregations were sort of used more for tiny little things, like for example, just saying during like a PageRank computation, how many nodes change their PageRank value. So each node would just sort of fire off a 1 or a 0, did I change? And the top level master would aggregate those values, and you just get one single integer, and there was no problem with that. But eventually aggregations got bigger and bigger and bigger. Specifically, one algorithm that was interesting was when you have an algorithm like k-means clustering. K-means is sort of an unsupervised machine learning technique that you might use to do something like, for example, finding similar emails. So an email to, basically you have a whole bag of emails. Like imagine we're talking on the order of like all of Gmail or something. And you want to sort of classify which emails are like each other so that eventually when you know that this set of emails, when you should know that this set of emails is spam, then you know that this whole class of emails is actually all spam because they're like each other. So you might create all these features that describe an email, the length of the email, the number of times the word enlarge appears in it. All these sorts of things that you might think of might be useful sort of features. And then you get this big feature space and you get this high dimensional thing. I'm not a machine learning guy, but that's about all I know about it. And you want to cluster on that. In academia, there's sort of a lot of different ways of doing k-means clustering in parallel. There is actually some message passing techniques and whatnot, but there's actually another technique where basically you don't actually send any messages at all. You just consider those, the clusters, the centroids, as the aggregators. What this means is that each aggregator itself is actually a high dimensional point. So then at this point, the aggregators themselves become very, very big. So initially, we stored the aggregators in Zookeeper. That obviously broke down very quickly because Zookeeper nodes, I think, can only store 1 megabyte or something like that. So that very quickly broke down. So we moved to storing them all in the master. And that worked pretty well for a while. But then again, it got larger and larger and larger, and the master became a bottleneck because suddenly everybody's sending to this one guy. This one guy is suddenly getting gigabytes of data and has to do something with it, and then it has to send it all back. So the real solution we came up with that scaled with us sort of to the future is that actually the role of aggregating data should actually be owned by the workers themselves. So basically, when the job spins up, we randomly assign each aggregator to a worker. So in this picture, each of these, the green, red line, are sort of the green, red, and black lines are sort of different aggregations. And as you see, they're owned by these 3 workers. And so during the computation, when a worker wants to aggregate some data, he knows who owns that aggregation. He sends it to that worker instead of sending it to the master. The workers then, the workers that are in charge of the aggregations, do the aggregations themselves. They send the final value to the master because there's actually an interface that we give you in the master where you can do something on an aggregation. For example, like in PageRank, PageRank might take millions and millions of cycles, millions and millions of steps to actually converge fully. And sort of the notion of convergence to you might mean like an epsilon of whatever it is. So you might make that decision in the master, say like, okay, epsilon reached within this value, stop the computation. So the workers send it to the master then sends it back to each worker that's in charge of it, but that data is very small because that's the final result. That's not the aggregation of every single value. And then the worker that's in charge of it sends it back out to everybody else so that everybody now has that state. So another thing that we came across was that basically in the BSP model, the sort of naive way to look at it is, again, that initial picture that I have. We split up the work. Each worker does its tasks. Then it sends the messages. So this is sort of intuitively what it looks like. If you take away that red box and you just have compute and network, this is sort of like the intro-level way to describe it. Obviously, for us, we know that all that time in the network is just time spent waiting. You're not computing anything. You're just waiting for messages to get delivered. And furthermore, initially when we built the system, we were basing it off like Hadoop's RPC and then a few other things that really just didn't fit with the model. We knew that what we're really doing is message passing. So clearly, the sort of RPC system and whatnot was not great. Clearly, synchronous calls are not allowed. We just want to send a message and fire and forget, basically. So the solution here was to put in this library called Netty. And Netty is a very high performance, asynchronous system that allows you to build sort of network services on top of it. And specifically, one of the things that we watch for all the time, that we track the metrics of, is we try and send when a vertex says, "Hey, I want to send this message to this other node," we send that message as soon as we can. We start sending messages as soon as we can, so that we interleave the computation with the network. And we constantly track that wait time, that red box, to reduce it as much as possible. And basically, what that ends up meaning is that we tune the buffer sizes of the Netty system to how many messages we buffer up before we send, and we also tune that in correlation with the number of threads that we use to run the actual computation. And one thing that we found is those tunings, along with basically almost any other thing you might imagine that we tune, like the GC settings itself, are actually very job specific. So we inside Giraph sort of pick like the smart sort of intelligence, the best sort of intelligent things that we can pick, but most likely for your particular job, if you really want to squeeze out that extra performance out of it, you'll have to do a little tuning yourself because we don't know your workload. We're sort of this generic system. So what does this all mean? What are the final results here? So this is a graph that's showing that in a given fixed data set, and that the data set we chose here was 2 billion vertices, 200 billion edges, and 20 compute threads. This means that per worker, we have 20 threads running that compute function on vertices in parallel. And what we did was we increased the number of workers, and we ran the exact same job, same sort of random data set, and we saw how does that scale. This graph might be a little deceiving because it looks like it sort of gets worse as it goes, but this is actually very, very close to ideal. If you look at the trend of that and you pick two numbers, say like 100 and 200, you can see that the values there are actually very close to like half of that. This is basically linear. It's essentially as good as you can get. Similarly here, we have the opposite. We fixed the workers, we fixed the computation power that we had, and we grew the data size. So we have 50 workers, 20 compute threads, and we increased the data size. By increase the data size, I mean specifically usually the number of edges. Sometimes the vertices too, but mainly it's the number of edges that you care about. Mainly that's the thing that really is the bottleneck. And you see here that the iteration time basically grows fairly close to linearly. And I don't recall exactly what that data point is, but essentially it's huge. It's billions and billions and billions of edges. So finally, what did we learn from all of this? And I hope that sort of you guys can take some of these lessons that we've learned and not repeat our mistakes and all the things that we did to get to this point. And this is sort of general knowledge that we learned from building this distributed system. So first one, and this one may be obvious, but basically doing coordination, doing fault tolerance and resiliency and all this is really a zoo. And personally, I think Zookeeper is actually one of the most amazing like open source projects there is in terms of things that are based off of Google papers. I think Zookeeper is based off Chubby or something. It really is amazing. It's like the piping that allows you to build, these fountains and everything on top of it. Secondly, doing something efficiently on the network is really, really very hard. And there's just no better library than Netty. If you're doing something and you care about performance on your network, you should stick in Netty and play with it. Thirdly, this is the one that I mentioned. If you're using a collection with primitives, you're going to get primitive performance. There's just no better way around it. And this is something that is unlikely to basically ever change because Java is very stuck in its collections API. And because primitives have to behave like objects in order to be used in a collection. So if you care about performance, again, check out a library like Fastutil. Fourth, byte array, though it may seem simple and it may seem sort of like C to you and it may seem a little scary, when it comes down to it, if you're going to create billions and billions of objects, you should really think of this. I think actually HBase does a similar thing. I think internally in their data structures, they use a lot of byte arrays too. Next, being unsafe sometimes is actually a good thing. Again, especially with things like the byte array. And finally, if you have a graph, you should try out Giraph. So, lastly, sort of the end-all result. We compared it with Hive. Our data scientists use Hive all the time to do graph computations. And sort of on the average job, this was the result that we saw. So 20x CPU speed up, but more importantly, around 100x elapsed time speed up. This means that a job that used to take 15 hours takes around 9 minutes. And specifically for those of you that just speak English and not math, at Facebook, data scientists, basically these jobs that they would run on the entire Facebook graph used to be called weekend jobs. And now basically they're coffee breaks. And I actually have a personal story of this that was very funny to me, where when internally sort of we were just, Giraph was picking up and we were starting to get more teams using it, we helped a lot of teams sort of port their Hive jobs to Giraph. And I had one guy come to me, and he was so used to the sort of the mindset of it being a weekend job that we finally sort of got the Giraph job working, and he launched it on like a Friday before he left work, because he was used to this, like, all right, I'll launch it, I'll check on it in Monday. Then Friday at like 10 or 11 o'clock, I get some text or page from him that's like, shit, man, listen, I think I messed something up. The whole computation is going to be screwed. We're going to have to start it over. Like, the whole weekend is screwed. I texted him back. I told him, your thing finished 4 hours ago. Like, it's already done. So then we reran it, and it was done by midnight. So that's it.